Alright, last video when we were doing factoring, we did show that x squared plus 5x plus 6 can be done as an unsymmetrical rectangle. It turns out to be an x plus 2 by an x plus 3 rectangle. But let me play with that. Let me play with that knowledge, because this is saying x squared plus 5x plus 6 is a multiple of x plus 2. Is x plus 2 times something. So let me look at this. So let me make this like a fraction I was doing before. X squared, whoops, messy board, plus 5x plus 6. If I tried to write this as a fraction, x plus 2, I should get out a nice answer. In fact, we can kind of see what the answer has to be, the other factor, x plus 3. So how could I do that? Let me do the algebra. In fact, let me do the same algebra I was doing before. I'm hoping, if I didn't know this fact, that this numerator is a multiple of the denominator. So I'm going to make that happen. In fact, I'll do each piece of the numerator turn, I'll make it a multiple of x plus 2. In fact, look at the first one, x squared. All right, keep that denominator there. X is really a multiple of x. I mean, x squared is a multiple of x. Sure, it's x times x. And I've got the rest of it. But my problem is, I don't want a multiple of x, I want a multiple of x plus 2. So I'm going to just make it happen. Make it x plus 2. Okay, there's my x squared, but now I've introduced a positive 2x. That shouldn't be there, so let me counteract that by going subtract 2x. Do you see what I'm doing? It's the same as I did before with those rectangles. So what I've really got now is x times x plus 2 minus 2x plus 5x, that's plus 3x plus 6, still over x plus 2. So I've at least made the first part a multiple of x plus 2. Now let me try to make this part a multiple of x plus 2. Right now it's 3 times x is a multiple of x. Not quite right. So I'm going to do the same work. X times x plus 2 plus 3 times, I'd love it to be 3 plus x times 2, but it's not. It's not. There's the 3x, but I've introduced a plus 6. So let me take away 6 to counteract what I had, and then I had a plus 6 still that I have to deal with. Yes, but here's the lovely thing. Zoom, zoom. It actually cancels out. That little extra error term disappeared this time. So this is really x times x plus 2 plus 3 times x plus 2, all waiting to be divided by x plus 2. So if I force my numerator to be a multiple of x plus 2, I actually see it is a multiple of x plus 2. X times x plus 2 divided by x plus 2 is just x plus 3. Cancel x plus 2's plus 3. And look, there's the other piece, just as we expected. Alright, that was one I knew was going to turn out nicely. So let's keep practicing the idea when we don't know what the answer is meant to be and see when we do and when we don't get multiples. Because we're now doing something called the factor theorem. When is a piece going to actually be a factor of what we want? When is the numerator going to be a factor of, have the denominator as a factor? That's the game we're playing now. So that was fast, but we'll keep going with practicing this. It will start to click, this clever algebra I seem to be doing. So let's do another example right now. Okay, let's try this question together. Is 2x squared plus 7x plus 3 a multiple of x minus 1? And if it isn't, how close is it to being 1? Okay, that's a strange question, but we can do it. I want to make this be a multiple of x minus 1. So I'll just go part by part by part, but I'll have some error, which I'll add to that. That will give me some error, which I'll add to that, and hopefully we'll have no error left over. Well, let's find out. So let's look at 2x squared plus 7x plus 3, and let me focus on 2x squared. Is 2x squared a multiple of x minus 1? Well, no, but at least it's a multiple of x. I can think of it as 2x plus x, times x, sorry, plus the 7x plus 3. But I really want it to be a multiple of x minus 1, not just a multiple of x. So I'm going to make it a multiple of x minus 1. Okay? But let's change the question, because there's the 2x times x is 2x squared, and I've got 2x times negative 1, I've got negative 2x. This actually brought in a negative 2x, which I shouldn't be there, so let me counter that with a positive 2x. So that's undone the change I've made. So I think we're still good. All right, so now I can see I've got 2x times x minus 1 plus 9x plus 3. That's now a multiple of x minus 1. But now let me focus on 9. This is 9 times x. Okay. It's a multiple of x, but I want a multiple of x minus 1. So let me make that 9 times x plus 3 and x minus 1. 9x is still there, 9x is still there, there it is, the 9x, but I've introduced a negative 9. I can't just throw in a negative 9 at random, I better counteract that with a positive 9. So now I'm seeing this is 2x times x minus 1 plus 9 times x minus 1 plus 12. And now I think I'm stuck. Now I think I'm stuck. So I'm seeing that this thing here, this 2x squared plus 7x plus 3, is a multiple of x minus 1. It's x minus 1 times, I'll just write something, I don't care what it is, plus 12. And my something is actually a 2x plus 9 detail. So it's almost a multiple of x minus 1. It's off by 12. Okay, so we found out what the error is. It's almost a multiple of x minus 1, but it's off by 12. Okay, that's the game I want to play. So I'll give you some strange formula like this, and we'll just work in turn, making each piece be a multiple of what we want, but have to adjust it. Have to adjust, and then off we go all the way down. And in this case, we've got a little error term at the end of 12. So let's do another example, because this is actually kind of fun once you get the hang of it. Getting the hang of it takes a little bit of while and practice, so lots of practice is good, but it will click eventually. Okay, let's do another example. Okay, here's a more advanced one. How close is x cubed? Okay, so away from our story of quadratics, but how close is x cubed minus 2x plus 1 to being a multiple of x minus 5? Don't know, let's find out. So let's go through each piece. X cubed minus 2x plus 1. Focus on the x cubed piece. I want to be a multiple of x minus 5, but at least to see it's a multiple of x, because I could think of this as x squared times x, a single x, and I've still got the negative 2x and the 1. But I don't want x, I want x minus 5. So I'm just going to make that happen. X minus 5. X times x, so x squared times x is x cubed, but I've introduced a negative 5x squared that shouldn't be there. So I'll counteract that by adding a 5x squared. So that's still good. I haven't changed the algebra then. All right, great. So there's a multiple of x minus 5. Now let me focus on, I guess, the x squared is the next term, 5x squareds. So I've got x squared times x minus 5 plus 5x times x. It's a multiple of x at least, but I want x minus 5. There's still a negative 2x and a plus 1. All right, 5x squared is a multiple of x, but I can make an multiple of x minus 5 by just making it a multiple of x minus 5. But what have I introduced? I've introduced 5x times negative 5. I've introduced negative 25x, so I better add 25x to counteract what I just did. All right, so I'm getting there. I've now got x squared x minus 5 plus 5x times x minus 5. Oh, now I've got 23 x's plus 1. Let me keep going. Let me focus on this term now. In fact, this is a multiple of x, but I want to be a multiple of x minus 5. So I'll just make it a multiple of x minus 5. So I'll do x squared x minus 5 plus 5x x minus 5 plus 23 x minus 5. But I've just introduced an error. There's 23 times x, yes. 23 times negative 5, negative 115, is that right? So I better add in a 115 to counteract that, and I've still got the plus 1. So I've got the number 116 at the end, and I think I'm stuck. I think that's my error term. That's close to being a multiple of x minus 5. In fact, I can see this as x minus 5 times a whole bunch of stuff, a 23, a 5x, and x squared, so I'll just write something. I'm actually not interested in that. And plus, I've still got my error term of 116. It is that close to being a multiple of x minus 5. That close. All right. But here's something interesting. Here's something really curious. That number 116 has to mean something. Surely that means something to do with the original problem. And look at this. If I put in x equals 5 into this formula, and the reason I chose that, if I put in x equals 5, this becomes nothing. Nothing plus 116. But if I put in x equals 5, I guess I've just proven 5 cubed minus 2 times 5 plus 1 would have to equal nothing plus 116. Whoops, which is 116. I think that's true. In fact, it is true. 125, take away 10, 115, plus 1 is 116. So the number you get here at the end is what happened if you actually put in 5 into this formula. All right, so the remainder's got something to do with the value of the expression at a particular number. All right, something's starting to click here. Let me write the previous one back on the board. We actually showed a previous quadratic. Let me write it on the board, clean the board, and we'll talk about this idea some more. Something's happening, something's going on. Back in a moment. Okay, here are the two examples we just did. We showed that 2x squared plus 7x plus 3 is almost a multiple of x minus 1. It equals x minus 1 times something plus an extra error term of 12. And this expression, x cubed minus 2x plus 1, did equal x minus 5 times something with an error term of 116. So what happens if you put in x equals 5 here? Put x equals 5. We got this as nothing. You get that 5 cubed minus 2 times 5, whoops, plus 1 equals 0 plus 116. True. What's an interesting x value to put in here? Be putting in x equals 1. So you put in x equals 1, you'll get that 2 times 1 squared plus 7 times 1 plus 3 would equal 0 plus 12, which I believe is true. Okay, here's what I think we've just proven. I think we've just proven this. In general, if I did say x minus some number, not just 1 or 5, I'll just call it h. A lot of people use h right now, I don't know why. But I've got some expression like ax squared plus bx plus c, maybe it could be even bigger like an x cubed or even x to the fourth. This will always equal x minus h times something, because you can do all the work we did, plus an error. And the error turns out to be really nice. It's the value of putting in x equals h into the original expression. Here's an expression. It will equal a multiple of x minus h, be x minus h times something, but there'll be an error term, and that error term will be the value of putting in h over here. Like the error term was the value of putting in 5 over here. The error term is the value of putting in 1 over here. So in general, the error term is the value of putting in h over here. This is beautiful. And here's the thing. If it turns out you've got 0 error, no error, that is putting in h into this formula that gives you 0, then you'll have no error and you'll have a perfect multiple. X minus h will be a factor of what you're talking about. That's the factor theorem. That's the factor theorem. So, I want to get a red pen because this red pen is very important. This is an important result. I'm going to write this in red. I'll be right back. Okay, got my red pen for this very important result. Here is the factor theorem. Factor theorem. If putting x equals h into ax squared plus bx plus c gives 0, that means it gives 0 error, then ax squared plus bx plus c is x minus h times something. On the nose, it is actually a multiple. So there, in very messy board technique, okay, you're used to my board technique now, I'm very messy, is the factor theorem. If a particular value makes a quadratic equal to 0, like putting in 7 makes it 0, then x minus 7 is a factor of that quadratic. If putting x equals negative 3 makes this 0, then turns out x minus 3, that is x plus 3, is a factor of the quadratic. This is amazing. We can actually now find factors by figuring out where this thing equals 0. Whenever putting in x equals h gives you 0, then you've got a factor. Basically, it's this purple idea with 0 error, and the error is what you get by putting in h. So if h gives you 0, you've got 0 error, you've got a factor on the nose. This is lovely, this is beautiful mathematics. We're being like theoretical mathematicians now, because there is a beautiful theoretical result called the factor theorem. All right, so we definitely need to practice this. Let me give you some practice problems, we'll do some more examples together, and we'll become experts. Good stuff.